Hello and welcome to this video on gradients of curves. So for a straight line such as y equals 3x plus 2, the gradient is constant, in this case 3. However, for a curve, the gradient varies. We no longer have a single value for the gradient. As you can see in the diagram, which is a diagram of y equals x squared, when x is negative 3, the gradient is negative 6, and when x is 2, the gradient is 4. Ideally, we want an expression in terms of x that gives us the gradient for any value of x, which is often known as the gradient function. The process of differentiation will allow us to find such an expression. At GCSE, we found the gradient of a curve at a particular point by drawing a tangent, which we explore further in this video. You may have already noticed a relationship between the value of x and the value of m in this example of y equals x squared. Just in case you haven't, here's a table of values. And looking at all the values in the table, it appears that the gradient is always twice the value of x, from which we may deduce that the gradient function is equal to 2x. We're now going to investigate this conjecture by calculating gradients of chords which sits closer and closer to the gradient of the tangent. We're going to work through the worked example from the textbook. So part A says the diagram shows the curve with equation y equals x squared. The tangent t to the curve at the point A, given by 1, 1, is shown. Point A is joined to point P by the chord AP. Calculate the gradient of the tangent t. So our solution, from the diagram we can see that as well as A, 1, 1, t also passes through 0, minus 1. Gradient is change in y over change in x. So substituting in our points, 1 take away negative 1 is the change in y. 1 take away 0 is the change in x. 2 divided by 1 is equal to 2. So the gradient of the tangent t is 2. Part B asks us to calculate the gradient of the chord AP at different coordinates for P. And you'll notice as you look at them that they're all getting closer and closer to our 1, 1 point. So starting with 2, 4, the gradient is 4 take 1 over 2 take 1, which is equal to 3. If we have P at 1.5, 2.25, then the gradient is 2.25 minus 1 over 1.5 minus 1, which is 2.5. When P is at 1.1, 1.21, the gradient is 2.1. And when P is at 1.01 and 1.0201, the gradient is 2.01. The final point they want us to check is written algebraically as 1 plus h and the square of 1 plus h. So the gradient is given by the change in y, which is 1 plus h squared minus 1, divided by the change in x, which is 1 plus h minus 1. Expanding the brackets, cancelling out the 1's, we get the gradient is 2h plus h squared over h, which cancels to 2 plus h. Part C asks us to comment on the relationship between your answers to parts A and B. So in the summary, in part A, we found that the gradient of the tangent t was 2, using actual points from the tangent. And then we looked at some chords. So when x was 2, the gradient was 3. When x was 1.5, the gradient was 2.5. And you'll see as we get closer and closer to the value of 1, as the extra bit we're adding on gets smaller, the gradient is getting closer and closer to 2. When we had x as 1 plus h, the gradient was 2 plus h. So as we can see, as h tends to 0, the gradient tends to 2. And this agrees with the result of the gradient function equaling 2x when x is 1, because 2 times 1 is 2. We'll be looking at this in more detail in the second video. Thank you very much.